Thanks everyone for coming. I'd like to talk about not aliens. I want to talk about distributed systems today. I want to give you this is sort of a crash course in foundations. And before I get started, a little word of disclaimer. A career in distributed systems is both exhilarating and frustrating. When things work, it's like a symphony. When they don't, it's like an 11th birthday party where half of the kids are on speed. I think that's a very accurate quote by Jeff Darcy from HKFS or CloudFS. And the reason I want to give this disclaimer, so I took a 3-month sabbatical at the beginning of the year, where I ended up reading a lot of distributed systems paper and really took all the time I wanted to always take and just read and read and read. And I think, distributed systems research and engineering is a very selfless act. Because what you do is that you sort of trade your sanity for the greater good of humanity, of understanding how distributed systems work. And you don't notice it. It kind of creeps in or sort of leaves you slowly. The way you see it. So just as a little disclaimer, if you come to me in 5 years and tell me, I know a lot about distributed systems now, but my life is in ruins, or the rest of it, I will have warned you. Just quickly about myself, my name is Manuel Bernhardt. I help companies to get started with reactive systems, or to keep them running, or make them run faster, or what's or not. I'm also a Lightband consulting and training partner, and my focus these days is mostly on akka cluster, akka streams. I'm also a scuba diver, and that's not the Danube. I live in Vienna in Austria, but that's not the Blue Danube. I wish it was. That is actually in Egypt. We don't actually have a sea in Austria. We just have lakes, and they're really cold, so it's not really good to go there to dive. It's sort of. And let me start with a motivational quote, another quote, you will get more of these. Life is a single-player game. You're born alone, you're going to die alone. All of your interpretations are alone. All of your memories are alone. You're gone in 3 generations, and no one cares. Before you showed up, nobody cared. It's all single player. I think it's a very beautiful quote by Naval Ravikant. And are you all motivated now? Is it, yeah? Does it work? Yes. Yeah, we can do this, right? So really this quote is maybe more to motivate the talk than to motivate you. Although if it does, that's great. Because if you think of a single node in a cluster, it's all single player, We think of a node, of a cluster as this set of nodes that talk to one another, but the reality of it is a little bit different. This is what I would call the God view of a cluster. We see all the nodes, we know they're there, there's S1, S2, S3, we know all of them. But if you actually build distributed systems, the way you have to think about it is from the point of view of the single node that gets to see other nodes over an asynchronous, unreliable network. And maybe there is a network partition and then you don't see the other node anymore, or maybe the node has a garbage collection going on if it's a Java node and it doesn't respond to signals anymore and you don't know what's going on. It's all very uncertain. It's all very much undeterministic. And it's one way to reason about these things that this sort of point of view which makes it quite difficult to build reliable distributed systems. So if we want to build a cluster, what do we need? We need 3 things. We need to discover who else is there with us in the cluster. I joined the cluster, but who is there? Who are the members? I need to be able to figure out that some node has a problem, that there is a failure. If there is a crashing node, I don't want to continue pretending it's there. I want to know about this. I probably want to know about it rather faster than slower. And finally, one of the reasons I might want to use a cluster is that I don't have enough computing capacity on one machine, and I want to balance that computing sort of out on different nodes for different tasks, maybe depending on where they're located. All of this load balancing aspect is also one of the very important things that you have to think about when you're building clustered systems. Now it turns out that there is one quite powerful abstraction that covers all of these cases, and that's the abstraction of group membership. So if I have a service that runs on each and every node, and that tells me who is there, who is failing, who has capacity to take up more work, etc., that is something that I can use to build an application on top of on these machines that sort of feels a bit more like an application that runs on one machine. Not exactly the same, but it gets easier. And if I want to implement such a group membership service, I need three things. I need failure detectors, I need dissemination, I need a way to spread the word out throughout the cluster, and I need consensus. I need to reach consensus. And so these are the three things we're going to explore today. And the first one is my favorite topic. I don't know why I have an irrational interest in these things. Who can tell me who this album is? What this album is? Yeah, that's great. This Wish You Were Here from '75. I think this actually depicts failure in action. And so let's talk about failure detectors a bit of theory here to get started with. So there's two key properties in failure detectors. The first one is completeness, which is to say that when a node crashes, all the other nodes in the cluster should know about the fact that this node has crashed. So if it's not complete, then someone will still believe that the node is there, and that's not good. So that's completeness. It's the first thing we want out of a failure detector. The second thing we want out of a failure detector is accuracy. We don't want false positives. We don't want healthy nodes to start suspecting other healthy nodes of having failed. And that are the two main things that we're concerned with. Now it turns out that in practice, there are real-life concerns, pesky little things like speed and network message load that we have to think of when we implement failure detectors, and that play an important role. So let's start with seeing how we could do that. The first wall we're hitting is an impossibility result. So in distributed systems research, we don't know so much what we can do, but we know a few things we can't do. And one of the things we can't do is to build a failure detector algorithm that can be both has completeness and accuracy at the same time if we run that over an asynchronous unreliable network. And we only got these asynchronous unreliable networks, so we can't do that. So what do? We make trade-offs. That's one of the things we do. We have to make choices. So we talk about strong to weak completeness, where all or some non-faulty members detect a crash. And we talk about strong to weak accuracy, when there are no or some false positives. And in practice, applications go for strong completeness and choose a weaker form of accuracy. That's what most applications go for, because the scenario where they have to deal with nodes that think that the other node is still there, that's a lot harder to sort of go around. So they go and prefer to sort of have a flakiness in the failure detection. There's two strategies for failure detection. One of them is heartbeats. So if you don't receive a heartbeat from a node, you sort of start assuming that it's gone. There's another one called ping pong. So you go and do a request response kind of thing. You send a ping and you expect a pong back. That's what Akka cluster uses, the ping pong, going back and forth. Now let me talk a little bit about failure detector types. The first I want to talk about is the phi adaptive accrual failure detector, which has obviously a very cool name. And it's an adaptive failure detector, which means it tries to adapt to changing network conditions, link quality, etc. And what phi does, it introduces the notion of accrual failure detection. So rather than saying, look, this node is gone, or it's there, this binary view, it gives the failure detector computes a suspicion value. And with that value, as we'll see, we'll be able to make more informed decisions. So this was made popular by Cassandra because they tried out a few failure detectors and they needed something that scaled for hundreds of nodes. and that's how it got more and more in the mainstream. What you can see on the graph here is for small thresholds you have a very fast detection time. For higher thresholds you have a slow detection. You have a slower detection time, right? Conversely, if you have a low threshold, the failure rate, the mistake rate is much higher than if you have a higher threshold. So there again, you have to make a trade-off. So the original paper says that there is a sweet spot between 8 and 12. In my experience, if you run on AWS, you want to go for 12, 13 or more, because that's just, I'm not going to continue talking about that, but that's just how it is. And here's an example how the idea of this failure detector is, say you have a master node and some worker nodes. So what you would do there is if the master sees that one of the workers has the suspicion value getting higher than 8, you stop sending it new work because maybe there's a problem. If it gets higher than 10, you could say, okay, this guy is in trouble. I'm gonna start rebalancing their work to some other work, and then above 12, I'm just kicking it out. I'm removing it from my cluster. It's not there anymore. And so this is the initial idea behind this accrual failure detection. I think in practice, especially for some applications, things happen so fast. You've got an interval, a ping interval that's so fast that you can't really use this. It's not really used in practice. So you sort of have to find which spot you want to use for your network. Turns out again, if the link quality changes throughout the day, you end up with a lot of flakiness. There is another adaptive accrual failure detector, which is the new one. This one is, so it's faster than Phi. It's slightly better, but also the biggest difference with Phi is I found it did well or better than Phi in cloud environments where you don't really have a network, but you have a virtual network or something like that. And it's also a lot easier to implement. So the value is a lot simpler to compute. So I implemented this one for Akka cluster and run a few experiments on it. And it's nice, but it's not, you don't get that much of a gain. It's still an adaptive accrual failure detector. Nothing has changed. So here is a new one. And that's the swim failure detector. As you swim lazily through the milieu, the secrets of the world will infect you. And swim is rooted in biology, in infectious diseases. It actually cites it cites quite a few papers that come from the biology, and so the idea is to just infect people. So swim is not only a failure detector; it has two components. It's got both the failure detection and the gossip component, the dissemination component in it. So here I'm talking about the failure detector part of it. And the idea is they wanted to build a protocol that scales well and not exponentially so or linearly so for many nodes. It's not because you have a bigger cluster that you end up with having to wait longer or things like that. And there's a few ways in which Swim does this. So one thing it does is that members that have a problem are first suspected, but they're not immediately removed. And then the suspicion spreads through gossip, and if the node gets it, it can say, "Hey, I'm still there. Don't remove me." It can go back and say, "I'm still there." So that's one of the techniques. The other technique is the one of indirect probing. So we ping. We choose one. We chose one node at random that we want to monitor. Then we ping it, and then that guy was running a garbage collection because it's a Java process, and so the ACK is too slow and it doesn't make it back in time. So instead of right away suspecting it, what we do is that we send a ping request message to other nodes, randomly chosen as well, and they go and they probe that node. And then maybe one ACK makes it back, and then we can ACK back to the original node, and we know it's there, okay? And this happens in one protocol period, and it's quite okay, and it reduces, all of this is just to reduce the amount of false positives. Now it turns out that in practice, so this paper is from, I think 2002 or something, it turns out that that nowadays on modern data centers, Swim doesn't do well enough by itself. And the people at Hoshi Corp figured this out. Hoshi Corp, they're doing Terraform, Console, Vault, all of these DevOps kind of tools. They also have clusters. And they implemented Swim, and they found that Swim was not doing so well in terms of failure. Like there were too many failures still. False failures were, what they say about failures is false positives, right? There were too many false positives in Swim. So they have this implementation of a membership service called Member List, which is written in Go, is open source. And it's an extension to the Swim protocol. It has 3 techniques that it uses, and if you add all of them and use all of them, what you end up with is drastically less false positives. So you're at less than 2% in comparison to vanilla Swim. And I think, by now I haven't found anything that's more state-of-the-art than this and has better results in real-life applications than this for the moment. So this is pretty much the state-of-the-art that I found. And yeah. So, I think we're through with failure detection. I mean, I could go on for more hours, but I don't think I have that time. So let me go for the next topic. Anyone knows this album? That's Pulse, from '95. I think it's a live album, so that's maybe why. And I think Pulse is really, translates well to this idea of disseminating, spreading information. So what do we need? We need to talk about members joining, members leaving, and members failing. This is sort of the information, the basic information we want to spread across about in a cluster when it comes to membership information. Okay. And then there is a few strategies. The first one is Multicast. And we have a problem with Multicast support. Because we just don't have it, okay? We have it in theory. There is IP multicast. There is even network, like hardware level multicast. There is UDP multicast. But none of this is readily accepted. If you go to see your sysadmins in a data center and say, hey, can we have UDP multicast? They go like, no. So multicast is not something that's readily available, and even if it were, we would still have this problem of how do we get things in order? Like if we need to keep ordering between different multicast messages, we end up, there is this very nice 50 pages survey on total order broadcast and multicast algorithms by Xavier Defago and Eyal. So, this one is sort of shows you a glimpse of what it means to reliably work with multicast. So that it's hard, it's still not there, so we don't have it. So what do we do instead? You ask, well, we go back to the year 2000. Anyone remembers Napster? You can download these music files in this MP3 format that was new and all legal and free. And so it turns out that because of peer-to-peer, there was a lot of research done with the same thing. Because what you have in peer-to-peer systems is just a big ring or a set of big rings, and you still want to search for your files everywhere. So how do you get the word across? How do you search? How do you pass things on? How do you and that's where all these gossip protocols were developed. And gossip protocols, the basic idea here is, and you don't see the animation because this is a static PDF file, but what you would see is normally a node, or maybe there is something like, no, there isn't. Anyway, what you do is at each tick of the clock, one node sends the gossip to another node. At each tick of the clock, at protocol period 1, you would have one node sends a message to the first one. Then at tick 2, both nodes will send the messages to other random nodes. At tick 3, all 3 nodes that got the message send it to other random nodes. So at the end of the day, what you have is in a very few ticks, you spread the word across quite fast. Okay. Now that's the oldest form of random gossip. For failure detection in this case. And there is more structured ones because random is not very deterministic. So what you have is round robin, for example, where you go and spread things in a round robin fashion. Then there's a binary round robin, which is a little bit faster. And also round robin with sequence check, which lets you sort of know when a gossip message should be arriving, and if it doesn't, then you can take some action. Now, for some reason, this idea hasn't caught on. So this paper I found it quite nice, but some reason I haven't seen this technique being used at all in modern systems. They just all go for random gossip. Maybe that also has to do with, all of our new cloud stuff. We just add and remove nodes, and there is a lot of randomness in there anyway. So these more deterministic approaches to doing things doesn't quite work. And then there's a third thing we can do. We can piggyback on another protocol. So that's what Swim does. It's called this infection style gossip. So in Swim, you have a failure detection component, which has a protocol. The protocol is ping, ACK, and ping requests. So we have these three types of messages, but there's still a bit of space left on the messages. Okay, so that's just a header that says what type it is, but then you still have some space in the message. So you fill the rest with gossip information or with a subset of the gossip, and that way you sort of spread bits and pieces of the data that you want to spread. You piggyback on top of these things, and I think this is very nice way of doing things because you don't have to introduce special gossip messages. Okay, you don't add more overhead, but you just end up having gossip there that just piggybacks somewhere. But then you ask, what do you even gossip about? And one thing we can do is say, look, this is node A. A has seen A 0 seconds ago. I am node A, so I know that I'm there. I always know that I'm there because I'm A. I have seen B 1 second ago. I have seen C 3 seconds ago. Now node B may have another view of the world. It has seen A 3 seconds ago. It has seen B 0 seconds ago because it's B, and it has seen C 1 second ago. Okay? And if these two were to exchange their gossip, what I would end up with is A has seen A 0 seconds ago, B 0 seconds ago, and C 1 second ago. We merged this information, and by merging this information, we have now an updated gossip message. And this gossip merging is something extremely common that is done in many things. In this example, this is failure detection gossip. And what you would do here is, if in one of these tables you end up with a last scene that crosses, 5 seconds or 8 seconds or something like this, you would end up just kicking that node out because nobody has seen it after 8 seconds, so we can assume that it has failed. There's a few gossip optimizations that we can do. Akka cluster does, for example, keep and maintain as part of the gossip a list of nodes that have received a certain version of a gossip. That means that when a node is about to gossip, what it will be able to do is to say, hey, these other nodes probably haven't seen the gossip message yet, so let me talk to them rather than to the ones that I know have already received and seen the latest version of the gossip. Akka cluster also speeds up gossip when less than half of the members have seen the latest gossip. So this can happen, for example, when you're starting the thing up, or when there's a network partition, everything is a bit shaky. So what you have there is just a way to spread things faster, okay? To reach convergence again faster. Convergence is when everybody in the cluster has the same idea of what the cluster is or should be, when everybody has seen the same information. And then in Lifeguard, they have an anti-entropy mechanism. In Lifeguard, so Lifeguard is the Swim extension, and Swim by default uses UDP to sort of gossip things about. And that sort of is a bit, there is entropy happening there because UDP messages can get lost, especially when the network is unreliable or unstable. So what Lifeguard does is sometimes it picks one node, picks another node at random, and does a full TCP sync of the gossip state over the TCP link, which is more reliable, and that way we reduce the entropy, and that really helps in sort of recovering post network partition, makes things faster. And that's about dissemination. Now that brings us to our third and last topic here. And does anyone know what this album is? Momentary lapse of reason, very nice. And I think that is an accurate description of consensus. So consensus, reaching consensus in a distributed system, that's hard and has driven many people insane, including me at times. And let's start with an impossibility result, the one of group membership, which is unfortunate because we try to have a group membership service, but it's not possible. Which is to say that group membership with a single group, or primary partition it's called, is impossible when there is at least one node that is suspected of having failed. So from the moment on that your failure detector says, hey, this guy is maybe there, maybe not, you can't readily assume that there is only one group left. And you could, for a very long time, the research community was like, but you know, maybe, just maybe, if we ignore that node and the rest happily moves on, we're good. And this was disproved in '96 that on asynchronous networks, you can't have that. You will end up with several partitions. And that's the problem of this split brain where you have many partitions or different partitions or everybody goes in their own little cluster of one node, especially on AWS. So we can't have this, and what we have to do again is sort of trade-offs. But one first thing that we're going to do here is, or that we shouldn't do, is we should not make membership-related decisions, like things like adding nodes to the cluster or removing nodes from the cluster while there are nodes that are suspected of having failed. Because if I remove or add things, then suddenly my cluster has a different view of the world. Some nodes will think that these are the list of nodes. Some other nodes will only think that there's another list of nodes. So I'll end up with a split view of the world, and then I'm in hell. Then it's really hard to recover from that. So don't don't let nodes join, or don't let them leave when you're in trouble. So how do we reach consensus? What do we do? One first thing we do is we need to reach consensus on time. And time, so there is one paper. So if there is only one paper, if I can interest you a little bit in this, if there is only one paper I would invite you to read at some point when you have time, it's this one. It's Leslie Lamport's Time, Clocks, and the Ordering of Events in a Distributed System. This is one of it won an ACM award. It's one of the most important papers in computer science, I would argue. And this is about how do you order things on different machines and processes that run on different machines. How do you establish a partial order between events? It also introduces the notion of a replicated state machine, which is used, we'll talk about it, in consensus protocols. It does a lot of this very foundational thinking in terms of how we can build distributed systems. And Lamport clocks are basically a logical clock where events get flagged with a certain version, and then we can establish a partial order between them. Now, Lamport clocks on their own are not enough. We need more. So what do? Well, we just make vectors of Lamport clocks. And these are called vector clocks. And what you can do with this, you can establish orders between events, and you can also flag concurrent events that happen at the same time. And these two things are quite powerful, and they're not to be confused with two more things, which are version vectors and the more recent dotted version vectors, which are extremely same, and often people sort of say they're the same, but they're not, because version vectors are concerned with conflict, like replicating data and detecting conflicts in replicas. It turns out that both of them have extremely similar semantics, but they are different. There's a blog post that you can read about it, that version vectors are not vector clocks. And there is a subtle difference in sort of the implementation, in the sort of garbage that these things produce. And And just to show you at least one line of code during this talk, and to show you that all that I'm talking about here is not just theoretical things, this is Akka cluster's gossip message. And what you can see there is that the version is a vector clock. So when the gossip moves around in the spread around across this dissemination, and when two, so the way it works, we have ping pong sort of, we sort of exchange the gossip, and when the gossip gets sort of together, the version the vector clock tells us, is this a more recent version of the gossip than I have? Is it the same one? Is it an older one? If it's the older one, I send back the newest version of the gossip. Or is it the same version? And then I have a conflict. I need to merge things. It's the same version, but the information in the message is not the same. So I can detect a conflict. I have to act upon that. So it's really used in the real world. Okay, now another tool that we have at our disposal is replicated state machines. Someone working with state machines here? A few people. I mean, any sufficiently complicated model class contains an ad hoc, informally specified, bug-ridden, slow implementation of half a state machine. Very nice quote by Pete Ford here. I think, state machines are really underrated tools that I don't understand why we don't use them more. Akka has great support for, finite state machine actor. It even has a persistent FSM that's also nice. And so let me give a few examples here. Again, I don't have the GIF. That's a bit. This should be an animation here. So let me just animate it with my arms. So let's say I have a client here, this red thing or orange thing. And these three things are servers, and each server has these boxes is a state machine. So what I would do here, I want to store a value in a fail-safe way. So what I do is I send an event up to one of these server nodes. I send the set of events that I want to save, and then what the blue things are doing, they're replicating the events in the same order using vector clocks, for example, to the two other ones, and each of the three nodes will apply the same events in the same order to the state machines. So these three state machines will end up having the same value because they apply the exact same effect in the same order everywhere. And that way we can store things in a safe fashion. If I have a 5 cluster node and I lose 2 nodes, I still sort of have my data there, my value being saved. And this is a very sort of, again, this was introduced in Leslie Lamport's time clocks and the ordering of events in a distributed system. And it sounds really nice. And now how do we implement it? Well, the way we implement it, to implement it, we need a consensus protocol. And, in 98, Lamport published this paper, The Part-Time Parliament. It introduces Paxos. And then at a conference later on, people told him, we don't understand how this works. So he sort of rounded up a group of people and said, hey, this is how it works. I'm explaining it to you. And out of this explanation that he made, he had this other paper in 2001, Paxos Made Simple, which sort of explains Paxos in a simpler way. And then 13 years later, there was a new paper published called In Search of an Understandable Consensus Algorithm. So it seems that Paxos Made Simple wasn't simple enough. And Paxos is a really nice brain teaser. It's hard. So Paxos is one of them. Raft is one of them. Raft is really like was designed to be understood and taught. And yeah, it does that. It's simpler. It's easier to understand. And then there's a very nice one that just came out. It's 2 months old. It's brand new. It's CAS Paxos. And CAS Paxos gets rid of the log. So usually in Paxos and Raft you have a log, and it's called replicated state machines without logs. It's a very nice approach. There's one implementation in Go. And it's still very new. So I expect we'll see more of that spreading out. I think this has quite a nice potential here. So this is sort of consensus protocols is stuff you may have heard of before. They're pretty traditional in their way of reaching consensus, but there is a more modern, a different branch of reaching consensus, and it has another different type of semantics, and that is the one of having strong eventual consistent consensus. Let's say it's using strong eventual consistency, and these are CRDTs, conflict-free replicated data types. There's two families. They're the ones that use the commutativity of operations and the ones that use the convergence of state. And if you want to use the ones that commute, where operations commute, like 1 plus 2 plus is a commutative operation, I can say 1 plus 2 is the same as 2 plus 1, okay? If I use these classes of CRDTs, I need a reliable transport, because if I lose an operation, it doesn't matter if that it's commutative, I just lost. The other one is convergence, based on convergence of state. This is what you see here. So we all the nodes start with the value 0. And then the first node up there sets the value to 1, and the second one sets the value to 4. And then we propagate that value down. And the convergence function that we're using here is the maximum. So the maximum on the third here, down there, this one, it's the maximum of 0 and 4 is 4. So we end up with 4 there. And then the maximum between 1 and 4 is 4. So at the end of the day, we end up with 4 everywhere. So we have converged using this max, and there is no room for conflict. We don't end up in a situation where we could have something else than 4. And this is very nice, because especially when you have a network partition and both sides get stuff written in them, when you converge back, you're going to converge back to the same value when the network partition has recovered. So that's quite nice. A lot of very interesting research in that space. It's still growing strong, this one. My favorite one is reaching consensus by conventions. So for example, a practical example here, in Akka cluster there is a leader of the cluster, a leader of the pack, but it's not elected. It's designed, and the way it's designed is by ordering. So you take all the nodes all the members in the cluster, you order them by IP address, and you put the ones that are not fit for being a leader, like the ones that have an inappropriate status, at the very bottom. And then you take the first one. And all the nodes do that, and so they end up with having the same idea of who the leader is, but they haven't talked about it at all. They haven't exchanged information. They just use this convention. The same is used, for example, if you in failure detection strategies, when you use the heartbeat approach, where the lack of message means that there is a lack of it's gone. So that this sometimes not sending data is as powerful as sending data. So this is a very nice way of reaching consensus that I quite like. So let me talk a little bit about Akka cluster. So Akka cluster, at the bottom you have the membership layer that takes care of telling who is there, who is not, who has failed, etc. All of these things. On top of that, we have several modules. For example, we have distributed data that is using CRDTs for spreading values out, replicating data in the cluster. We have cluster singleton, so we run one singleton in the whole cluster, and it takes care of sort of balancing it over if the node on which the singleton lives crashes. On top of singleton, we have cluster sharding, where we want to share data across many nodes because there's too much of them. Data, or actually actors in this case. Also very well managed there. On top of that, you build your application. So you have all these tools. There's more of them. I just mentioned these ones, which are quite interesting. And yeah, there's routers that I should add to this thing, like cluster-aware routers that know about the cluster and it can do load balancing and adaptive load balancing depending on the load of each machine. So Akka cluster uses the phi adaptive accrual failure detector. It uses a ping pong strategy for failure detection. It uses actually a little bit modified version of phi, which also takes into account the fact that the JVM has garbage collection pauses. And then sometimes, well, you have to adjust things, let's say. In terms of dissemination, we have random gossip, but it's biased towards the nodes that may not have seen the latest version of a gossip. In terms of consensus, the leader is leader by convention, and the membership decisions are driven by the leader, joining and leaving. This is quite important, we'll get back to it. Or let's put it like this. The leader in Akka cluster will not let new nodes join in the traditional sense of things when there are nodes that are suspected of having failed, and the same thing for the leaving part, at least in one definition, in one of the semantics. So let's look at what happens if we're in a happy path, if everything goes according to plan. What happens is we're joining, then the leader decides that it's okay, we can join, now we're up, and then we want to leave, so we're in the leaving state, then the leader says, yes, now you can leave, so we're exiting, and then we're removed from the cluster, and everything works according to plan. And that's the dream. And then the reality is a bit different. In reality, things don't pan out that well, so what we have often, we join, we're up, then we become unreachable, that's the failure detector that detects that, this little FD thing here, there. Then we're going down, and then we're removed. Now, there is one thing here that you may notice, and that there is no leader here. There is no failure detector there from unreachable to down. This is where the magic happens. This is where the unicorns are. And this is where we have a very interesting class of consensus or protocols, algorithms that take care of this. And this is called split brain resolvers. This is a class of algorithms that you use to sort of automatically get rid of or take care of shutting down the right nodes in the right, like all of these things. So we're out of time. Sorry about that. So I won't be able to tell you about split brain resolvers today. But you can go on my site and read about them eventually. No, I think it would take just another talk entirely to cover that topic. That's why I don't even try and attempt to start. I think anyway I'm pretty much out of time. 3 minutes. So what I invite you to do is to read papers. These are the papers that have been harmed during the creation of this talk. Yeah, you can. I will put the slides online. You can see that. And yeah, that's pretty much it. Thank you so much. And we have time for 3 or 2 minutes, maybe time for questions.